Assalamualaikum warahmatullahi wabarakatuh. So welcome to Electromagnetics and Transmission Line, Chapter 4, Slide 2, Electrostatic. So we're going to continue on electric scalar potential, followed by electrical properties of material, conductors and dielectrics, and finally the electric boundary conditions. So electric scalar potential is actually the voltage between 2 points in a circuit, which is equal to the amount of work or potential energy required to move a unit charge between 2 points. So voltage here is the same meaning as voltage potential or electrical potential. So refer to the figure here. So when you have a charge Q, so the charge Q will exert a force Fe equals to QE in the minus Y direction. So it is actually going to the minus Y direction. So that's why you will need an external force F external, okay, here, F external, that will counteract Fe, which is the expenditure of energy in the positive Y direction. So the work done under these circumstances is dW. So dW here is equal to F external, which is in the positive Y direction, dot dL. So this would be equal to minus QE dot dL. The differential electric potential energy dW per unit charge is called the differential electric potential. So when you have dV, that would be equal dW over Q, which is the differential electric potential energy over the unit charge. And this would give equal to minus E dot dL, and you will have this in terms of joules per coulomb or volt. Next is the potential difference. So imagine you have 2 points, P1 and also P2. Okay, so that would be equal to the integration from P1 to P2 dV, which would be minus E dot dL. Sometimes the potential difference is called as V21, which is equal V2 minus V1. The electric potential energy that a unit point charge would have when located at that point. So usually when you have Vp, okay, the voltage potential, is equal to the integration, negative integration from infinity to P E dot dL. So the electric field dot dL in volt. So it is common to assume the reference point, which is the zero potential, is at infinity. So the potential in that case is the absolute potential. Conservative field. So whenever you see V21 is equal to 0, that means that it is conservative. So there are 3 possible conservative field. Okay, number 1 is when the charge never move at all. Number 2 is the charge move in a closed loop. And finally, the charge is moved to a point with the same potential, where V2 is equal to V1. For a point charge, we may calculate the potential as V2 is equal to V1. So when you have V potential is equal to minus integration of E dot dL from infinity to that point P, we'll have the final equation as Q over 4 pi E naught R in volt. For multiple sources of electric field, the potential obeys the superposition property. So if you have V1, V2, V3, which are the potentials due to the charges Q1, Q2, Q3 respectively, so the total potential V at that point would be the summation of all the potentials. For continuous charge distribution, the electric potential can be found by replacing Q with dQ. So imagine here, before we have 1 over 4 pi E naught Q over R. So you just have to replace Q with rho L dL, rho S ds, and rho V dV for line charge distribution, surface charge distribution, and volume charge distribution respectively. Now, equipotential lines. So it is actually a method for visualizing the electric potential. So this technique is similar to the contour lines used in showing heights in maps when lines connect points of the same height. Equipotential lines are contour lines along which charge move with zero work. So the potential is the same along the line. In 3D, the equipotential lines turn into equipotential surface or spheres. Now, electrostatic field is a conservative field. So that is, to move a charge in a closed path within the field need zero work. So these are the properties of conservative field. So number 1, the integration of the closed surface E dot dl is equal to 0, okay, for any closed loop. Number 2, the integration from B to A, E dot dl, is independent of path for any given endpoints if you have point A and B. Number 3 is del cross E, or the curl E, is equal to 0 everywhere, meaning that it is an irrotational field. And finally, E is the gradient of some scalar. For example, E should be equal to minus del V, or the gradient of voltage. So all conservative field can be represented by a scalar function. In electrostatic, the field intensity can be represented by the scalar potential, which is equal to E minus gradient V, or minus del V. So here's a recap on how you can find the gradient of the scalar field. So you have gradient F is equal to del F, and this would give df over dx x hat plus df over dy y hat plus df over dz z hat. So this is for the Cartesian form, and for cylindrical and spherical you have it like this one. Okay, so r hat, phi hat, and z hat for cylindrical, and when you have r hat, theta hat, and phi hat for spherical. Now, from the differential form of the Gauss's law, which we have learned earlier in the previous slide, so del dot E is equal to rho V over permittivity. So inserting E is equal to minus gradient of V, this will give you minus rho V over permittivity. Next, we have electrical properties of materials. So the electromagnetic constitutive parameters of a material medium are its electrical permittivity, E, magnetic permeability, mu, and conductivity, sigma. So you have these three. So material is said to be homogeneous if its constitutive parameters do not vary from point to point. It is isotropic if its constitutive parameters are independent of direction. So materials can be classified as conductor, semiconductor, or insulator. So here you have the constitutive parameters, the electrical permittivity, which is represented by E, magnetic permeability, which is represented by mu, and finally conductivity, which is represented by sigma. Okay, these materials can be divided into three. So first one is conductors. So usually it is metals. Okay, so metals are conductors, very good conductors. So the conductivity is very high, which is around 10 to the power of 6 to 10 to the power of 7 in Siemens per meter. And then you have semiconductors, which is still a conductor but much lesser than the metals. And finally is the dielectrics or insulators. Okay, so the conductivity is very low, which is between 10 to the minus of minus 10 to 10 to the power of minus 17. So in Siemens per meter. So dielectrics is the opposite of conductors.